that small glitch, and so I'll make it full screen, and here we roll. So hello everyone, I am here to present some concepts about speech processing paradigms, which will cover the journey of speech processing from starting from signal processing and coming now as to the deep learning methods and all, methodology and all. So this seminar is towards the AIML school, ODIA AIML school, and once again, welcome to the talk. So a little bit about me. I'm Ravi Shankar Prasad, and I have been working as a postdoctoral researcher at EDF. Currently, I'm in India. I'm collaborating with EDF. I'm also collaborating with CSEM Neuchâtel and Aalto University, Finland. Prior to that, I did my doctoral thesis in analysis of dynamics of focal track system using zero-time windowing method in IIIT Hyderabad. My thesis supervisor is Professor Yagnanarayan, and my research interests span across speech signal processing. Recently, I have developed interest towards physiological signal processing and machine learning algorithms. Are you also getting some interference? I'm getting some sound interference.
Yes, yes. Now we can continue. I think one of the students actually.
Okay.
Yeah.
So a little bit about evaluation of speech technology over time. So the journey of speech processing, it dates back as early as the 1800s and 1700s era. And the first speech machine was created by von Kaplan, and he created a acoustic mechanical device which was able to produce certain vowel sounds. The idea of the device was that it was comprised of different cavities made of wood, and then from one side air was pumped into the device with different thirsts, and that resulted into speech like sounds. So it was one of the earliest attempts to create speech uh, by humans, sorry, mechanical speech by humans. And moving forward, a century later, Thomas Alva Edison, he created the famous dictation machine, which was created to record speech and then playback later for further uses. The dictation machine was comprising of a metal cylinder, which was made of copper, and it used to record speech by making grooves on the copper cylinder, and it was later able to play back.
Sorry to interrupt. I think Ravi Shankar, PPT is not visible.
Really?
Have you shared the PPT? Your screen is visible, but PPT is not visible.
I'm sorry about that. How do
I share the whole screen? Okay, share the whole screen.
Is the PPT visible now?
Yes, now it is visible. Yes.
Oh, I'm so sorry about that.
Yeah.
So basically, I started here where I say that I'm here to present about speech processing paradigms, and then I told a little bit about myself, and then we moved on to understanding evaluation of speech technology over time. Okay, so everything now okay by now?
Yes.
Right. So I was talking about the earliest machines which were developed to record and create speech or synthesize speech. So first known machine was created by von Kaplan, as I told that it was an acoustic mechanical device on which air was pumped from one side, and based on the cavities and their structures, sound used to come from the other side. The main sounds which were created were vowels mostly, based on different size and shape of cavities. Later, a century later, Thomas Alva Edison, he created the first dictation machine, which was able to record and then playback speech. The dictation machine comprised of copper cylinders on which grooves were made while speech was being recorded and it was being playback. So after a while, these copper cylinders were replaced by wax cylinders, but nonetheless, they were quite useful in playing back mostly meetings, speech, which was recorded over meetings. And later it became more popular when it was used to record audio like music and other things. Then after another decade, almost another decade, Bell Laboratories came up with a machine called Audrey. This was when the advent of transistors happened. Solid state devices which were based on earlier transistor were based on the vacuum tubes, and that was used to create Audrey, which was able to recognize spoken digits with 90% accuracy as the claim. But the crutch was that it was only able to recognize the digits when it was being spoken by a single speaker. The journey continued while IBM created another device called Shoebox using similar architecture, which was able to understand or recognize English words, mostly like 16 English words, basic words like yes, no, and other things. Okay. When the advent of semiconductors happened, transistors came into picture, and then CMU created Harpy. Harpy was basically one of the, at that era, it was one of the smart computers which was able to recognize more than 1,000 words and also some phrases. And then the journey continued as more and more standards keep pouring in. And today we are living in the era where Apple, Siri, and Google and Amazon's speech recognition systems are standard. So this is a little hop on ride towards the journey of speech technologies. Now, apart from speech recognition, there are other problems in which speech technologies work, and they try to solve some tasks. So we know that the most prominent speech technology we use is automatic speech recognition. Further to that, one of the more popular technologies is speech synthesis. Speech synthesis is popular for systems where you need computers to interact with humans. These could be IVR systems or announcement systems. These could be personal digital assistants as well. So speech synthesis also faces a lot of challenges where the synthesized speech is supposed to be as natural sounding as possible, and it should also contain the natural elements of speech, such as modulation of the amplitude and modulation of the pitch frequency, modulation of the prosody. So all these things. Apart from that, we also try to extract linguistic and paralinguistic information from speech. Linguistic information is based on the language that is being spoken. A lot of it comprises of natural language processing tasks as a post-processing module, and paralinguistic information such as state of the speaker, gender of the speaker, age of the speaker, also like emotional state of the speaker, also like what is the health pathological state of the speaker. So all these information speech can divulge to us. So all in all, speech is a very mystical signal which we produce, and it contains all this, it encompasses all this information in itself, and somehow we are trying to demystify it, or we are trying to learn it. So speech contains volume of information about linguistic and paralinguistic content, and its information identification and processing of this information is trivial in humans, because we have developed the production and the art of production and perception of speech over thousands of years. As my professor used to say, that reaching to moon was faster to us than producing speech. So it has took us a lot of time to develop this sophisticated production and perception system. And that is what we are trying to translate to machines using different paradigms based on signal processing and paradigms based on machine learning. So that's what we are trying to do in speech related activities. A little bit more about speech production mechanism. We have to understand how the mechanism works, what are its different components, to understand how to dictate machines to identify and demystify these components. So basically, speech is a resultant of modulation of air, modulation of air released from lungs, and this modulation takes place through different cavities. So what happens is the air filled in the lungs is pushed out, and through the trachea and the vocal oral tract, the speech comes out. Okay, so we can see here in this diagram that lungs and other articulators which take part in speech production are they work in unison. So lungs are there, and then the trachea is there, and through the trachea we have the vocal folds which are placed here at glottis. We'll learn more about it, and then the air crosses pharynx, and then through oral and nasal cavities, sound comes out. So this whole system comprises of different components which are non-linearly combined. Why I am saying non-linearly? Because the modulation, the degree of modulation that is happening at different stages is non-linear in nature. And there are articulators which are static and dynamic in nature. So static articulators do not move, while dynamic articulators constantly keep moving during the production of speech. Like take for the example our jaw. The upper jaw is a static articulator. It doesn't move during the production of speech, while the lower jaw keeps opening and moving and changing its shape. Okay. Similarly, tongue is another dynamic articulator. So these dynamic articulators, they move voluntary or involuntary. Why I say voluntary? Because we have muscle control over voluntary movement. Involuntary, when the articulators move under the impression of inertia. Like let's say if you are holding your tongue high for some time, due to gravity and its own weight, it is going to come down. It's going to settle down. So that is involuntary movement, and that affects speech production as well. So similarly, there are very small components, lot of small components that move involuntary also. So speech sounds are broadly categorized as voiced or unvoiced. We will learn about these sounds. So overall, the production of speech involves transmission of information which is generated in the brain, and through the brain and neurosensory mechanism, this transmission comes to the motor sensory mechanism, and the motor sensory mechanism helps moving the articulators in a certain way so that speech is produced. Okay. So the inherent inertia of different articulators along with the motor behavior imparts a stochastic behavior in speech. Because this is non-deterministic motion, the resultant signal becomes stochastic in nature. So that is why we say that we cannot produce the same sound twice practically, because it is impossible to take all the articulators and go through the same dynamics again to produce the same signal. Okay. So speech production is somehow modeled as a concatenated tube structure. So this array of concatenated tubes, we can see that the speech production mechanism can be modeled something like this, where each tube is of different length and different cross-sectional area. This imparts a different resonance characteristics to each tube, and therefore whatever input this goes through this tube and whatever output it comes out through this tube is a resultant of multiple modulations that act on this input. And because we do not know exactly what kind of modulations are acting on the input, the resultant speech signal becomes a heavily complex, convoluted resultant of interaction of this source and the system. So any input to this kind of a concatenated tube structure is known as the source. Okay, and I'll explain what is the source in the production, what is actually the source component in the production of speech. But we just understand that, let's assume that this is some kind of a structure which when excited results in a sound, and this excitation when it changes, it results in a different sound. And this structure is also dynamically changing with respect to time. So as we see that this particular diagram shows that the oral cavity is a concatenation of different tubes, and also the nasal cavity is also being drawn as a concatenated structure of tubes, which is cavity and which is connected by the velum. So the velum, I'll show in further coming pictures where the velum lies and how it controls the coupling of the nasal cavity to the oral cavity. So this is basically it will give you an idea to understand how we can uh, understand the production of speech. Okay, so um, moving to different kind of sounds, as I told you in the previous slide that there are two major categories of sounds. One is the voice sound and another is the unvoiced sound. So voice sounds are basically characterized by their high amplitude and periodic behavior. Okay, so when we see a speech sample, we can easily make out what is voiced and what is unvoiced just by seeing as the signal behavior. The signal behavior is more periodic and more structured in voiced region, whereas it is more noise-like and aperiodic in case of unvoiced sound. So voice sound is periodic because it results from a periodic vibration of the vocal folds. So we know that, we don't, even if you don't know, like there are vocal folds which are present at glottis. here is our glottis, which is lying right around trachea. And whenever we want to produce a voice sound like a, u, e, a, o, all these are voice sounds. And whenever we try to produce voice sound, the vocal folds which are present at the glottis, they vibrate periodically. They vibrate at a certain frequency, which is also known as the fundamental frequency of vibration. And this frequency, fundamental frequency, gives rise to a periodic output, which is modulated through the vocal tract, and this results in a voice sound. Unvoiced sounds do not involve the periodic vibration of the vocal folds, and hence they are more noise-like in nature because they are produced just by modulating the air gushing out directly from lungs without the involvement of vocal folds. So are things clear? Is everything clear till here?
Yes, sir.
Okay. Yeah. Are there any questions? Anything you want to revisit or clarify? No?
No, continue.
Okay. So basically, this is the basic difference between voiced and unvoiced sounds, which is the fundamental frequency of oscillation. The voice sound mostly comprise of vowel sounds, but there are other voice sounds also, which are like nasal sounds and glottal sounds, which make the whole universe of voice sound. The unvoiced sounds are basically the consonant sounds. That's why in every language we have vowels and consonants clubbed, like grouped differently. Okay, so because their production mechanism is fundamentally different. So now a little bit more about the voice source characteristics. So the oscillation of the glottis is generally captured using a device called electroglottograph. And this electroglottograph is basically a couple of electrodes which is placed on the glottis. And this is the electroglottograph or the EGG signal. This is the corresponding speech signal, a segment of voiced speech signal. And this is how the EGG signal looks like. So we can see that there are periodic oscillations in the EGG signal which dictate different phases of the EGG cycle. So one cycle of EGG basically comprises of the impedance going up and down. This is basically the impedance between the electrodes that is being captured. So this impedance goes high and low during one cycle of EGG, sorry, and this represents the opening and closing of the glottis. So the glottis is vibrating, the vocal folds are vibrating like this. They open, they close, they open, they close. And the closure is quite abrupt. So the vocal folds, they open under inertial stretch and they close abruptly. So this abrupt closure of the vocal folds is known as the glottal closure. And this glottal closure, whenever it happens, the time point is known as the glottal closure instance. So this glottal closure instance can be seen in the difference EGG. When we take the gradient of this EGG signal, we can see that there are sharp peaks in the gradient which show a very sharp change of impedance whenever the glottal closure happens. So this dynamics of the gradient of the EGG reflect that the glottal closure is quite sharp. And because the glottal closure is quite sharp, it produces enough energy to produce that sound. So the energy which is produced by the sharp or the sudden closure of the vocal folds, this energy is then modulated by the oral tract or the nasal tract to produce a sound. Okay, so it is therefore the voice sounds are characterized by high energy, whereas the unvoiced sounds have lower energy, that we'll see. So a little bit okay, I'll explain how unvoiced sounds are produced. So as I told, like whenever we want to produce voice sounds like vowel ma, sorry, a or oo, so we have the vibration of vocal folds which can produce louder sounds. But unvoiced sounds like sh, s, all these are like fricatives, or also like p, p. So all these are unvoiced sounds and they are produced by just brushing the air without the vibration of the vocal sound. So these sounds are low amplitude or low energy in nature. So this is a fundamental difference between voiced and unvoiced, that is the periodicity and the amplitude. There are other differences. which are explored using further analysis. So a little bit more about system characteristics. So the speech production system, the whole production system, basically, as I told, that it comprises of different articulators, and starting from the lips, the lip region is known as the bilabial region. Then we have the labiodental region, which is beyond the teeth and between the lips. And then there is the delta region, which is the teeth. And then there is the alveolar region, which is just behind the teeth. And then palatal, which is the ridge, which is totally under the teeth. Okay, where we can understand where palatal is whenever we put our finger inside our mouth, and we can see that there is some ridge which has a ridgy kind of structure, that is palatal. And then there is velar region, where the velum lies. Whenever we open our mouth wide open, we see that there is a velum hanging. Okay, which whenever we put extra pressure on the velum, it comes down and it couples the nasal tract, and hence nasal sounds are produced. So whenever we want to produce ah, vowels like ah, oo, the velum is up, and it decouples the nasal tract. So there is no airflow through nasal tract. But whenever we want to produce the nasal sound, we purposefully push the velum down, and we produce nasal sounds like ma, na. So ma and na are nasal sounds, where the energy flows through oral and nasal both cavity. Sorry, in the nasal cavity, and the velum is down. So whenever we want to produce nasal sound, we have to close the oral tract some or the other place. So if we want to produce ma, we have to close the oral tract at the lips. Mm. So this is ma. If we want to produce na, we have to close the oral tract at the alveolar, or the alveolar, which is just behind the dental. Mm, mm. So if we close it here behind the dental region, we get the sound n, 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 n. And if we close it at the lips, we get the sound m, m. So these are nasal sounds. Okay. So similarly, constriction. These are constrictions produced at different places, and also the coupling of the velum, which results in the nasal sound. Similarly, we can create construction at other places and produce other sounds. Like if we want to produce s, s, so we are creating a dental constriction. Okay, we have to understand that whenever we want to produce the fricative s or sh, sh, so in case of sh, we are creating a constriction at alveolar region. And if we want to produce the dental s, we are creating a dental region. Okay. So in Hindi also we have the Varnmala, where all these sounds are categorized based on their place of constriction. If we see the family of shs, we have like sa, sh, sh, where the constriction is different places, and we have air gushing through the lungs, and the vibration of vocal folds. If it happens, it's called voiced fricative, and if it doesn't happen, it is called unvoiced fricative. So the difference between the two sounds s and sh is that sh is palatal or alveolar, s is dental. But if we look at their voice counterparts, we see that if we put voicing to s, it becomes z. So voicing basically changes the nature of the sound. So s, which is a dental fricative, becomes voiced dental fricative z. So this is how different articulators change different sounds. Similarly, sh, which is an alveolar fricative, becomes zh. So when we try to add voicing to sh, it becomes z. So this is how different kind of sounds are produced. Similarly, if we have stop consonant where we constrict the vocal tract at some place, completely close it, like p. P is a bilabial stop, which is comprising of the lips closing down. P, and when we add voice to it, it becomes b, b. So p is without voicing, p, 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 and b, b, b is when we try to add voice to it. So this is how, like, this is a little bit of anatomy, how speech is produced using different articulators, and how different sounds are categorized. So the International Phonetics Association, which is also called the IPA, they have categorized different sounds based on their manner and place of articulation. So you can also Google IPA chart, and you will find the whole chart. I have taken only some parts of it, where it depicts different consonants and vowels. There are other sounds also which IPA have categorized based on their production dynamics. And here you can see like how you can produce different sounds. Like I have told you about fricatives, which like bilabial fricative, the left one is unvoiced and the right one is voiced. So we know that there is a bilabial fricative huh, huh, and its voice counterpart which is huh, huh. Okay. Similarly, this is labiodental and voice counterpart v. Whenever we add voicing to it becomes v. Okay. The manner and the place of articulation is the same. Manner has changed from unvoiced to voiced. Similarly, sh and z. This is unvoiced sh, post alveolar, as I told, and this is the when we add voicing to it. So these are different notations which IPA uses to depict different sounds, and these are phonetic notations. So phonetic notations depict different sounds by their acoustic properties. Acoustic means the inherent signal and spectral structure of it. Is everything clear till here? Or do we have any questions? I'll continue then. So similarly, different vowels are also categorized by IPA as open and closed vowels. Like A is a pretty open vowel, A, but when we want to produce vowel E, we have to really close the vocal tract, E. So E is closed, A is open. Similarly, E is front as seen here, but A is central. So front is the like where the constriction happens. Okay, central, A is central because you have to open it in the center. If you open it in the back, it becomes A. Okay, so these are different voice sound also categorized by IPA. Now moving forward to signal acquisition, speech is generally collected by as a pressure wave using a diaphragm and a microphone. Because the audible range of humans is 20 hertz to 20 kilohertz, the favorable Nyquist sampling rate used for speech acquisition is 44.1 kilohertz. But most practically, most systems they operate till 8 kilohertz. The desirable sampling rate of speech for implementing a lot of systems has become 16 kilohertz. So generally, speech is you if you collect speech using 8 kilohertz or 16 kilohertz sampling frequency, it is fine because you will get most of the characteristics. Why this is so? Because the human ear has less perception towards higher audible frequencies. So a lot of applications are derived on how human hearing behaves, and therefore they do not give much weightage to the higher frequencies. Therefore, the speech collected at 16 or 8 kilohertz is quite optimal for building practical systems. Okay, and speech characteristics in the spectral domain are studied using Fourier transform. We all know that signals are studied in spectral domain using some or the other transform because uh, humans have a comprehension towards temporal and spectral changes both. Because if we see light of different colors, it is only because we have a comprehension of different frequencies. Our visual comprehension of different frequencies allows us to see different colors. Similarly, we have auditory comprehension of different frequencies, which allows us to hear different sounds. That is why when we hear a concert, we know what instrument is playing based on its frequency behavior. Okay, when we want more bass, we increase low frequency behavior in our equalizers. So then we get more bass. Similarly, if we want more treble sound, we increase the high frequency content and we get more treble. So this is kind of a equalizer which is created by the Fourier transform basic, and we see that this is called the spectrum of speech. Okay, and we see that there is a envelope of the spectrum. So the spectrum can be seen by its gross and finer behavior. Okay, the finer behavior in spectrum gives us different peaks in the spectrum. So what are these peaks? These peaks refer to the fundamental frequency of oscillation, which is also seen here as f naught, and its harmonic. So whenever we have a voice signal, voice periodic signal like this, we'll always have the first peak as f naught if we do a Fourier decomposition. So first component or first peak component of the Fourier decomposition will be at the pitch frequency. which is also known as the fundamental frequency of oscillation of vocal folds. And this generally gives us the idea of speakers and different other characteristics in speech. So these other peaks we are separated by the multiples of fundamental frequencies like 2, F0, 3, F0, 4, F0, like that. So these are called the harmonic. And if we look at the gross structure of the spectrum, the envelope of the spectrum, there are global peaks in the spectrum, which are denoted by F1, F2, F3, F4. These are known as the formants in speech. These formants basically represent the resonance of the vocal tract. Okay, as I in the previous slide, I have shown that the vocal tract can be approximated as a concatenated tube structure, and each tube has a particular resonance characteristic attached to it. So this particular spectrum can be seen, the growth peaks in the spectrum can be seen as the resonance of the major tubes which are taking part in the production of speech. Okay, so these are called the formant frequencies. So now we know that how a Fourier transform or a spectrum obtained using a Fourier transform can tell us about the source and system components in speech. The source component is the F0 component, which is the fundamental frequency of the vibration, and the system components are formants. These formants are fundamental to understanding sounds. It is the location and their relative differences and their bandwidth of these formants that represent different sounds. So a vowel with certain formant structure will be different from a different vowel. Okay, so formant structures are different in different sounds. This we'll see later. Um, Also, the moving bit towards perception of speech. This is the mechanism of perception of speech where we hear the speech through our ears, and this auditory mechanism has three steps, three different parts, which is outer ear, middle ear, and inner ear. So outer ear comprises of the pinna, which is the pinna is right the structure which helps us localizing and different sounds, and then it goes to the eardrum, and then to this structure called cochlea. So cochlea basically acts as a filter bank to the speech we hear. Cochlea is a non-linear filter bank which weighs different frequencies with different amplitudes. So that is why our auditory perception is weighed in a different manner. So cochlea basically gives more weightage to low frequency sound. That's why the human perception to low frequency is higher. This is true for visual also. Like if the fan is moving slow, we can tell the difference between one velocity to other. If it is moving slow, if the frequency of rotation is slow, we can say that it is a bit faster than the previous or not. But if it is moving very fast, we cannot differentiate between two frequencies which are close enough. Okay, so this is similar to the sounds. If we hear low frequency sounds, we can differentiate between two close appearing frequencies. But if we hear high frequency sounds, we cannot differentiate well between two closely appearing frequencies. So this is the depiction of the cochlear scale, which is non-linear in nature, and we see that the low pitch sound is filtered at the very center of the cochlea where the length is longer, and the high pitches are filtered on the outer structure where the length is where the length is longer for high pitches. It means the resolution for high pitch sound is lesser, whereas the resolution for low pitch sound is higher. So our hearing mechanism or the auditory mechanism is biased in such a way. So is everything clear till here? Now moving forward to analysis of speech. As I told you that the Fourier spectrum helps us to analyze speech, and this is a famous way to visualize speech, which is also called the spectrogram. So spectrograms are also called the pictured speech, and there are two types of spectrogram which we can create depending on the analysis size of the segment. So here is a speech segment. If we take a speech segment of analysis duration, say 10 millisecond or 20 millisecond, we can derive the Fourier characteristic, and then we move that analysis window every 5 milliseconds, and this is the spectrogram which we get. If we take a longer analysis window, we get something called as the narrowband spectrogram, which is denoted by the figure B. A narrowband spectrogram has a good frequency resolution. Frequency resolution is good means it can give you different bands and it can give you how much of energy is distributed in different bands. So a narrowband spectrogram can give us different pitch frequency and their harmonic peaks. We can see that there are horizontal lines here in the narrowband spectrogram giving us a good frequency resolution as to where the harmonic peaks are occurring. But it has a bad temporal resolution. It means that over a period of 20 millisecond or 10 millisecond, it will show us the same constant behavior of the pitch frequency and its harmonic. It will not change generally because the analysis window duration is larger. If we make the analysis window duration shorter, then it gives us something called the wide band frequency spectrogram, wideband spectrogram. And the wideband spectrogram has a good time resolution because the analysis window is shorter, but it has a very bad spectral resolution. That's why we get these fatter bands or thicker bands where we see that, okay, in this particular, let's say 0 to 1 kilohertz, our energy is moving something like this. In 1 to 2 kilohertz, there is a dearth of energy. And then again in 2 to 3 kilohertz range, there is some energy distributed. So unlike in narrowband spectrogram where we have almost 10 bands in 0 to 1 kilohertz, we only have one band here in 0 to 1 kilohertz in wideband spectrogram. So different kind of spectral resolution can be attained with different analysis window while performing speech analysis. And then this also gives us different information, like here in narrowband spectrogram, we can gain information about the pitch frequency, we can gain information about the harmonic and their location, and also towards the finer band structure in case of unvoiced sounds. Like here we see that there is a noise like structure and their noise is present in higher band frequency. But here in the wideband spectrogram, we can see the formant peaks in a better way. So here we can see the F0 peak and harmonic peaks in a better way. In wideband structure, we can see the formant peaks in a better way. So different spectrograms gives us different information, which we utilize to represent the speech production system. Now moving on to parameterization of speech. Speech is usually parameterized by Mel band frequency, Mel capstral frequency, capstral coefficient. So this is a speech signal which gets us to the magnitude spectrum. What we do with magnitude spectrum is speech is produced by a convolution of source and system. And we know that because it is too convoluted system, a structure, it is too complicated to deconvolute these two components. So we cannot simply deconvolute source and system together because speech is a very complicated resultant of a very complicated mechanism. So what we do is we try to deconvolute it in the capstral domain, something called as the capstral domain. Now, what is the capstral domain? We take the speech, we take the magnitude spectrum as given by the Fourier transform, and here are the peaks in the magnitude spectrum, which are resultant of the source and the system. So we see that in this Fourier spectrum, the source component, they vary quite swiftly, and the system component are more static in nature. They appear as global peaks, whereas source component are varying quite quickly. So we take the so what we do is we take the magnitude spectrum and we decompose the magnitude spectrum using again a Fourier transform. So this gets us from the spectral domain to the capstral domain, which is like spectral domain is when signal is transformed using Fourier transform, and capstrum is when the spectrum is transformed back to another domain using another Fourier transform. So this is the capstral domain, and in the capstral, sorry, this is the log magnitude. I'm so sorry. This is the spectrum and this is the log spectrum. And when the log spectrum is transformed to the capstral domain, we have two components here. One is the low coefficiency component and another are high coefficiency components. So high coefficiency components basically are fast moving components in the magnitude spectrum, which are related to the source, and the low coefficiency components are the system related components. So in this capstral domain, the convolution of source and system in speech appear as a linear superimposition. So it becomes a linear addition, and we can simply separate the source and system components here in the capstral domain by just dividing the coefficiency axis. Okay, so this is why capstral analysis is quite popular in speech because it changes the non-linear convolution to somewhat linear superimposition. Okay, so then based on this capsular domain analysis, there is a very famous parameter which is called the MFCC, which is derived from speech. So we take the speech signal, we do some pre-emphasis, de-emphasis for boosting the high frequency component, and then we do some framing and then windowing, and finally we take the Fourier transform and the magnitude of the Fourier transform, and we create something called the Mel filter bank. As we see here, the Mel filter bank has good resolution at low frequencies. So there are a lot of filters in the low frequencies stacked together. So these frequency filters are very close to each other. That's why we have good resolution in the low frequency. Whereas in high frequencies, we have coarser resolution. So this is the Mel filter bank, which is created on the human auditory perception scale. And then applying this Mel filter bank to the capsular coefficients and performing a IDCT, inverse discrete cosine transform, we get something called the MFCCs. MFCCs are representation of the source and the system characteristics, and they're very popular for almost all speech related applications. So this is how we get MFCCs from speech. There is another parameterization which is quite popular, which is also called the linear prediction analysis of speech. Linear prediction analysis do not assume any do not use the Fourier decomposition. Besides, it assumes a source filter model of speech where the filter comprises of all pole models. So all pole means it has multiple resonators. So linear prediction assumes that the filter model or the vocal tract system is comprising of different resonators, and then it tries to decompose speech into source and system components. So I mean, it's a very complicated theory. If we want to get into further, you can discuss. We can discuss it offline. But here something we attain from LP analysis. So the blue component is the linear prediction system component, which is derived, and it is all the Fourier spectrum is also plotted to show us that the system peaks are indeed captured in the LP system component. Okay, so the resonance peaks in the spectrum, Fourier spectrum, are captured using the LP system component. So LP can be linear prediction can be performed for different orders. Here is a lower order linear prediction which gives us an approximation of only 4 peaks here, whereas a higher order linear prediction gives us approximation of multiple peaks. But this is also overfit for because all these peaks are always not relevant. Some of these are harmonic peaks, which are not system components. Basically, these are mostly source components. So this is how the linear prediction decomposition happens for speech to derive source and system components. So this is called inverse filtering of speech. So what speech is a result of convolution of a source filter model where a source component, which is either the vocal fold vibration or the noise through the gushing of air, it acts on a system components and gives us speech. And linear prediction is used to decompose speech into these two components, where the linear prediction residual is known as the source component, and the linear prediction system component is a concatenation of different resonance peaks. Okay, that's the system component. So this is also used to parameterize speech because the linear prediction gives us formant peak, and the formants and the source both are used to parameterize speech. I would like to highlight here that linear prediction is one of the fundamental concepts that is still used, very much relevant to parameterize speech and towards speech coding. The speech coding which we use in current telephone and mobile scenario is based on linear prediction only. It was introduced by Rabiner in 1978, but it's still very relevant, and a lot of speech coding is happening on this. Moving on to the holy grail of speech processing, the automatic speech recognition system. Automatic speech recognition systems are basically the transcription systems where we speak to a machine or a computer, and the computer is expected to produce the corresponding utterance in a desired language. Now, ASR systems are basically uh, a, a pattern matching problem. Okay, ASR is trying to address a pattern matching problem where we have a set of hypotheses, which is also called the word hypothesis WK, and these are basically sentences in a desired language. And what we are trying to do is we are trying to match the input speech segment to one of these utterances, and we are trying to find whichever is the best matching hypothesis. Now this gives rise to a scenario where many questions come up. Like, first of all, how we are going to match a signal to uh, utterance this thing, like utterance representation. So it means that we have to create a common ground where textual representation and signal representation can be matched. So how do we convert a signal to its optimal representation, optimal sequence representation is the first question. How do we convert the word hypothesis to its optimal sequence representation, which is B? The signal has an optimal signal sequence representation A, and the word hypothesis has an optimal sequence representation B. And how there are two problems: how to convert these into another domain, like how to convert S into A and W to B, and then how to match A and B so as to find the best matching hypothesis. So the ASR system tries to answer this question based on different paradigms. So I think there is a lot of text here, but I would like to just say that uh, in one of the paradigms, which is known as the knowledge based paradigm, what we try to do is we try to extract the acoustic phonetic information in speech and try to match it, translate it, or map it to something called the phone sequence or the phoneme sequence in speech. So we take the signal and we just analyze its properties. We can do it using Fourier decomposition, using spectrogram, you can using LP analysis, using the formant information, using the source information. We take all that information and try to see that if speech can be mapped to its phonetic information, which is a sequence of phonetic information, which is A. And similarly, we take word hypothesis like a set of certain utterances, and then we try to match it to its linguistic representation, which is B. We also do it in NLP based tasks where we create graphemes for a language and we try to map it to its syntactic and phonemic information. Okay, so there is something called the phone set we create, and we map speech characteristics to its corresponding phone set. We map the linguistic information to its corresponding phone set, and then we use DTW or dynamic programming to match these two phone sets. Okay, so this is how ASR is trying to address the speech recognition problem. And whenever we find the best mapping for A and A to B, best matching for A to B, we say that that word hypothesis is true. Okay, so a little bit about this, like the knowledge based approach. I told you that the symbol set for speech is the phone set, the shared latent symbol set, where both in linguistic information and acoustic information are to be matched, is called the phone set. The spoken utterance is matched to the corresponding phone set using acoustic phonetic knowledge. The transcript is mapped to phone set using linguistic knowledge, and the two phone sequences are matched using string matching, as I told. So uh, in 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 speech recognition using statistical modeling, the mapping of acoustic information to its corresponding phone set is done using probabilistic models. The Bayes model basically helps here a lot, where a wide hypothesis, where a particular word hypothesis, the probability of identifying or seeing a word hypothesis giving the signal is mapped to a joint modeling of the word and the signal hypothesis together. So I'm not I'm not going to read out these equations, but what I'm trying to say here that for a statistical modeling, we try to use statistical tools to jointly model the word hypothesis and the signal domain so that we can understand or identify which particular phone set or element of the phone set maps properly to the signal. So we use HMM or yeah, somebody has something to say. I'm sorry, I'm going just on and on. I mean, is everything clear till here? Like, do you want something to be revisited or? Everything is clear till here? Everything's going fine?
Yeah, at the end, Ravi, you can take questions.
Okay, okay. So I'll keep going on and on.
Yeah, yeah.
All right, thank you, sir. So what we try to do is we are trying to create a mapping from the spoken utterance to a certain grapheme set or the phone set. So we use now we use HMMs or even deep learning tools to create that mapping. Okay, so hidden Markov modeling basically is a very famous tool that has ruled automatic speech recognition domain for years and years, decades and decades, and which was very fundamental to ASR domain. The HMM basically understands speech as a time signal, a time varying signal, and it hypothesizes that each each frame or each frame of the signal is created by a certain state of a underlying Markovian model. Okay, so it sees speech utterances at output of a certain state sequence, and it tries to build a model which can depict this speech state sequence properly, optimally, using probabilistic models and also using the Viterbi algorithm. And then it based on this hidden Markov modeling, we can depict what we can map the given utterance to its one of a phone representation or the grapheme representation. It's a very if I keep elaborating on ASR systems, I mean it will still be a drop in the ocean. So if you want to gain more insight into it, we can take it offline. So this is the whole cycle of ASR systems based on statistical modeling, where we take speech signal, we do some front end auditory processing like creating MFCC or LPCC coefficients out of it or filter bank coefficients out of it, and then we take that representation and then we feed it to a likelihood estimator that creates the phone mapping from the MFCC or other parameters which we have created. So the phone mapping is created here using the Gaussian or neural network classifier. Once we have the phone likelihood or the phone mapping, then we send it to the decoder, where based on the linguistic information like n-gram model and also the grammar information, the phone mapping is decoded into an intelligible speech. Okay, and then it is used based on the semantics is parsed into a proper utterance. Okay, so maybe you guys know more about this part better than me, but I'm trying to just say that we use HMM and DNS to create this phone mapping, which is a likelihood for the given speech frame or utterance or the parameter set of parameters, and then we map it to a proper sentence. So yeah, this is the pipeline of a general pipeline for ASR systems. Okay, now moving on to the other problem of speech synthesis. Uh, speech synthesis systems are also like they use heavily rely on NLP systems to create meaningful speech out of text. A very robust and dynamic NLP pre-processing unit is used to parse the linguistic information to a phonetic representation, so that these phonetic representation can be mapped back to the acoustic signal. So it is almost inverse of what we do in automatic speech recognition. So the synthesis systems are also known as TTS systems. They're text to the speech systems, and based on the NLP tasks such as normalization, phonetic analysis, and prosodic analysis of the speech or of the text, like we do we take the phonetic input and map it like phonemic input to and map it back to the signal domain. Mapping it back to the signal domain is straightforward. As I told you about linear prediction analysis, we have a filter model, we have a source model, we just convolute them back. So this filter model is basically obtained from a mapping of the phonetic information to the signal information. So the phonetic information is mapped to the signal information based on this filter model. And then we use the source model to excite this filter model to result in the speech spectrum or the speech signal. Okay. So this is like totally inverse of the ASR system. So Yeah. So this is the same thing, like where we vary the source and the source characteristic between voiced and unvoiced. If we are using a voice source, it is generally taken as a sequence of impulses, because I told you the glottal closure systems are very sharp in nature. They are usually modeled as a sequence of impulses. So the source is modeled as a sequence of impulses. In case of voice sound, in case of unvoiced sounds, it is modeled as noise, and then it moves. It goes into a gain control, and then we take the linear prediction filter to synthesize the speech. So concatenative speech synthesis is another speech synthesis where we take speech segments which are taken out from a human speech, human utterances, and then chunks of it are concatenated according to the linguistic information. It does not contain much of complications as in term of generation of speech, but there are complications involved where concatenation leads to boundary errors and other errors like prosodic errors and other things. So it is one type of speech synthesis, concatenative speech synthesis, where we take chunks of speech signals and arrange it accordingly. And there is another way of speech synthesis called the articulatory speech synthesis, where we have models of different articulators and we move it according to the textual and the prosodic information, and then we generate speech. And then formant based speech synthesis, which I just explained, which is based on the linear prediction model, where we have the filter coefficients based on the formant information. The formant information is derived from the mapping, which is from the phonetic space to the formant space, and then we excite this filter using a source model, and then we generate speech. So this is how the speech generation takes place. Now, this was about the two major tasks in related to the speech applications, speech recognition and speech synthesis. Now, a little bit more about my project, which I have floated in this summer school, which is about the spoken term detection. Spoken term detection is basically identification of a spoken term or a utterance in a huge database of speech. So this is just like searching a textual query like Google search or something, but this search happens in the speech domain. Spoken term detection is also seen as an extension or a variation of automatic speech recognition, where we are performing pattern matching, but pattern matching is happening between signal two spaces where signals are kept. So here the word hypothesis WK are basically speech signals. So we are trying to match an input speech signal or input speech segment to another domain which comprises of the speech signal, unlike in ASR where WK represented word hypothesis. So spoken term detection is quite useful in recent days. We know that almost all voice assistants work or utilize spoken term detection because they have a limited vocabulary, and what they are trying to do is they are trying to see if the user is speaking certain terms or not. So implementing spoken term detection is low cost and easier for voice assistant because they have to perform only specific tasks like Alexa, raise the volume. Okay, so they have to detect if Alexa is said, so they have to detect the spoken term Alexa. If the voice assistant detects Alexa, then it records the next statement, raise the volume for me. So it will look for terms like volume, raise. So it will perform a task accordingly based on some natural language processing, and also rest of it is done electronically. So I'm just illustrating how important, what is the importance of spoken term detection in today's scenario, and how different devices, different technologies are implementing it as an integral part of their systems. Okay, so a little overview about what goes inside a spoken term detection system. The input speech segment is parameterized using short term processing, and then some features are extracted from that short term processing parameters. Similarly, you have word hypothesis or signal hypothesis, which is contained in the database. The database is used, and these are also parameterized after short term processing and then feature extraction. So these Y and K are features extracted from the signal database, where you have a lot of utterances kept in. And the Zs are the features extracted from the keyword, which we are trying to spot. And now we have to match Y and Z and see if actually Z matches Y. If actually the keyword is something which has been spoken as compared to the signal database. So this matching happens in the dynamic programming or dynamic time warping framework. Okay. And because speech is a time varying and very stochastic signal, we use variants of the dynamic time warping framework to match a signal to its counterpart, a keyword. Okay, so here's how the dynamic time warping looks like in case of a spectrogram or spectral information matching. So here is U1 is the utterance which has been stored in the data set. U2 is the utterance which is spoken by the user. And if you parameterize the utterance based on the spectral properties in the spectrogram, we see that the spectrogram is an array of frames of information, and we try to match these frames correspondingly using dynamic time warping, and we can see if the match happens, there would be a darker path from one utterance to another, and we can see that it's a perfect match. So this is the whole construct of DTW and spoken term detection, and this is how the project uh, uh, also would be taking place. And yeah, that's about it. So I think that was all about the brief overview of speech processing and different applications. So that's all from my side in terms of presentation. Thank you. And
Thank you.
do we take questions now?
Any questions, participants? Either in chat box or you can unmute yourself and ask.
Yeah, so Ravi, actually, I have pasted your project in this link, in the chat link. If you want, yeah, you can open it, no problem.
Yeah. So this one. So is this, I'll just, I think I'll have to share the entire desktop. That's what they said, right?
Yeah.
Okay, anyways. So is this project visible?
Yeah.
So mine is
Your is a project. Your is project number 5, MP5.
5, right? Audio keyword spotting. That's my project. So this basically explains you that audio keyword spotting or spoken term detection, these are synonymous and they are used for. So there, this is like they initially it is uh, generally approached using large volume continuous speech recognition task, where the latent domain is the phonetic domain, where the utterance and the query are both using ASR system. They are both converted into phonetic string, and the string matching takes place, which is quite intuitive. If you want to identify acoustic keyword or audio keyword in a certain database, why not convert the whole database to text and use the query convert to text and then search in textual domain? So this is quite intuitive, but there are issues with that kind of approach I have explained there. And then we approach it by using something called query by example based method, which is what I showed in my slides, where we take the utterance, parameterize it. We use the feature space to parameterize utterance and the spoken database, and then match it in the feature space using dynamic time warping. So this is called query batch example based method, and a little taxonomy of the approaches which are generally used in spoken term detection and what we are going to do in this project. So if someone is interested, we can discuss more about it offline. And yeah, I can also show you a little bit of demo of what I have showed in my slides. So if you give me another 5-10 minutes, maybe I can. Shall I?
Yes, yes.
Yeah. So here is a very popular tool which was developed in KTH Sweden, one of the leading laboratories in speech processing in the world. It's called the Wave Surfer. It's freely available there. You can just type Wave Surfer on Google. You will get Wave Surfer toolbox from, I think it's from SourceForge. It is uploaded on SourceForge. Earlier, it was hosted on their own website, KTH, but now it is on SourceForge. You can download it. You can use it to analyze speech. It's very convenient to use and it gives you a lot of information. So here is the, can we see Wave Surfer? Is it visible?
Yes.
So here is how it works. So we open a sound sample in the Wave Surfer. So here is a sound sample which I have downloaded from Timid, and I also have the transcription of the sound file. So I import this sound file. When I try to import or open a file in Wave Surfer, it gives us options of different sampling rates, sampling encoding, and also different offset and other things. We can just choose the whatever is the default setting and just click OK. And then it will ask me what kind of information do I have or am I trying to open. So if I just want to open a waveform, I'll just scroll down and choose a waveform. Okay, I press OK, and this is the waveform which is present in the audio file, and I can simply select this by pressing mouse and select this part and delete it. So just press delete, and then we can see the waveform, the rest of the waveform has modulated, and now we can see different parts in the waveform. Here we can use this tool to zoom in. This is another tool to zoom in. Okay, so basically if we check this part, we can see that if we zoom into this part, we can see that there is a periodic structure which shows that this is the voice speech segment. Okay, we can see that this voice speech segment appears periodically, and if we move the scroller to aperiodic sounds, we can see that the unvoiced segment appears noise like. So we see that the voice segment has more amplitude, is more structured, and more energy is there present for voice segment, whereas for unvoiced segment we see that there is a lot of noise. And sorry, here is the unvoiced segment. Yeah, we can see that it is noise like, and it is also low frequency, low amplitude, low energy in nature. Okay, so we can see, analyze the difference between voiced and unvoiced, and we can just zoom out and we can create multiple panes. Like here, if I select a speech for 10 millisecond or 20 millisecond duration, we can see that I have selected, way too much zoom in. I have selected like 3 or 4 pitch cycles. Okay, 3 or 4 cycles are there, and if I just right click and create pane, and in create pane, which if I choose sorry, not create pane, spectrum section, if I choose spectrum section, is it visible, spectrum section?
Yes.
So if I choose spectrum section, a new dialog box appears. Is the dialog box visible?
Yes, yes, visible.
Right. So this shows us the spectrum, the DFT or the Fourier spectrum of this particular block of speech, which I have selected. And we can see here in this spectrum that there are pitch frequencies, there are peaks related to the pitch frequency. If I place my mouse here, I can see in the down pane, I can see what is the information at this particular peak. I can see that the frequency value is 234 hertz. So 234 hertz is the pitch frequency, and then double of it would be the first harmonic, which is 460 hertz. So 230, 460. So double of 230 is the first harmonic. Triple of 230 will be the second harmonic, 670. Okay, so these are harmonic peaks. So if we use the DFT spectrum, we can see the pitch frequency and its harmonic peaks across the spectrum. Okay, this spectrum is still 8 kilohertz because our speech is sampled till 16 kilohertz. So the Nyquist range is 0 to 8 kilohertz. So here is the analysis method. If I change the analysis method to LPC, from FFT to LPC, I see that I can gain the envelope based on LP analysis. And here is the order of LP. So if I change the order of LP to 10, I see that I get only 1, 2, 3, 3 peaks in the spectrum. But if I change the order of LP to 16, I get 1, 2, 3, and 4 peaks in the spectrum. So this is how, using Wave Surfer, we can change LP analysis, and then we can see how many peaks we can get. Okay, we can also click here, and if we drag here to this peak, we can see what is the distance between this peak and this peak. So dB is in the red, we get dB, which is the y-axis difference, the difference in the amplitude or the power of the peaks. So there is a 25 dB difference between this peak and this peak, whereas dF is change in the frequency. So there is a 1588 hertz difference between this peak and this peak. With this peak, if I place my mouse here, this peak is at 815 hertz, as seen in the last panel. The bottommost panel, we see frequency 815 hertz. If we add 1500 hertz to it, we'll reach here, which is 2400 hertz. Okay, so we see how Wave Surfer can give us difference between the peak frequencies and their powers, which is the dB. Okay, so this is the spectrum section. Now if I make it smaller, and then if I want to plot the pitch information, I can do a right click on the waveform. We go to create pane, and then we can create pitch contour. If we choose the pitch contour, it gives me the pitch contour across the voice region. So wherever voicing is there, it creates a pitch contour, and we can see that the pitch is ranging. If I drag it a little bit downwards, you can see the pitch range. Pitch ranges between 150 to 250 hertz. So this is like how the pitch changes. This is also called the prosody in speech. The rising and falling of the tone of the pitch gives rise to the prosody, where we see what are you talking about. So these are changes in the pitch which leads to the prosody, and this can be studied using this. If I again right click and go to create pane, if I create the formant plot, you'll see that there is a new spectrogram that has come up depicting 4 different formants. The red formant, is it visible?
Yes.
Yes.
Okay. So the red contour depicts the first formant, the green contour depicts the second formant, the blue contour depicts the third formant, and the yellow contour depicts the fourth formant. And we can see that for different sounds, the formant structure is different. Also, the spacing between different formant is different. Okay, as we go from one sound to another, if I just click this part, and then if I zoom in using this tool, you can see that the first format is for this sound is around 1 kilohertz. Okay, sorry, not around 1 kilohertz, is around 700 hertz. Whereas in this case, it is around 1 kilohertz. The second format is at least 1 kilohertz away from the first format. But here in this sound, the second format is closer. So different format and their dynamic, how they move close, how they move away, gives rise to different sound. Here we can see that this is the unvoiced section, which is quite noise-like. So here we have very low frequency energy and high frequency energy. So this high frequency energy gives rise to unvoiced sound, or unvoiced sounds are understood by the high frequency information. So this is how we can extract source and system information using Wave Surfer. Okay, so this is a little illustration of what all we can, what I have said in the slides, and what all we can understand from the speech domain. And then when we parameterize, when we derive this, we can also save this information. By the way, we can right click and save data file. If we save this information, we can save it in a txt file, and txt file will contain the values of the pitch with respect to time. Similarly, we can save the formant information. So if we have the source and the system information, we can create parameters and then use different models to perform tasks such as speech recognition, speech synthesis, or something like that. So this is a small demo of what I have told in my slides. Now I think if everything is fine, we can move to question answers, and if Anything needs to be revisited in the slides?
If anyone has a question, they can ask the questions. There is no question from other side, the participants.
Anyone having any questions? No questions. So Ravi, is there any data set is available for the low resource languages or for only English languages? This data set is available.
There are quite a lot of data sets available. It depends on what you like. When you say low resource, it means the resource is low. It means the data set is limited.
Okay, so somebody wants to create the data set. Suppose how I will collect this? What are the equipment?
If you want to create a low resource language data set, first of all, I would suggest that first of all we should understand what are the phones in that language set, and then we should create phonetically balanced utterances, phonetically and grammatically balanced utterances in that language, and then we get speakers to record those utterances in different. We have to, if we're curating the data set for low resource language, we should invite as much variety as we can, different age groups, different genders, and then different characteristics of the speakers. How many dialects we can variation in the dialects we can accommodate, and also like this has to go in two parts. First, we have to create the linguistic part where we should have utterances, we should have textual information which is rich in the phonetic content and also the grammatical content, the syntactic content. And when we have this, then we should focus on getting as many diverse speakers as we can get, and then we can get them to record different utterances and then create a database.
That you mean that suppose 100 sentences are there. Suppose I want to collect the data set for the 100 sentences only. So is it required to, I will take 100, say 10 or 20 different students to speak those 100 sentences, or one student is sufficient?
No, one student is not sufficient at all, because any system would be like to be developed on multiple speakers. Otherwise, it will be biased to one speaker. If we develop speech systems on one speaker, trained on one speaker, it will be biased to one speaker. There are ways to normalize speaker, but they are not optimal always.
Okay.
So if you have multiple speakers, that is very good. If you have more than 5 or 10 speakers, and also like of different genders, it is always a good mix and quite a balance. Because whenever we will be performing evaluation, also we will be keeping one speaker out for evaluation, for training and evaluating purposes. So that way also it will be helpful if we have multiple speakers.
Thank you. Later I will contact you.
Sure, sir.
Yeah, I have also same question. Like I want to continue. How about the sentence length? Like, so do you think you will prepare some kind of sentence? Will select some sentences and that will give to the volunteers to record it, or how big will be?
The thing is, like, see, you need someone who has the knowledge of the grammar in that language. So then we can create certain sentences where they are phonetically rich. It is very important to have sentences that are phonetically rich and balanced. If we leave certain fonts out, then while training systems, it will be biased more on the more available fonts, because the prior probability of certain fonts will be very high. So that's why if we are creating sentences for low resource languages, we will need someone who is well acquainted with the language, who can create sentences which are phonetically rich, syntactically rich. And then we can also see that these are prosodically balanced sentences. Like, not a lot of sentences are questioning sentences, like, where were you, what were you doing, type. They should be like more neutral sentences or something like that. So if someone has that kind of, someone who is a linguist in that particular knowledge language, or close, who has studied that language, it would be quite helpful for they to take their help and create sentences which are normalized. And then we can get them to recording.
And domain, like, is it how important is the domain? Like, when you select the sentences.
Domain, I didn't get. Come again.
Domain means like, for example, we'll select the sentences, example like common daily usage communication, or sometimes some sentences are from some literature, old literature. So uh, how the domain will be.
See, domain will
picture.
be important if we are doing language processing as well. If you are purely doing speech processing, like speech recognition or something, in that case, domain doesn't matter, because the source of phonetically richness, it doesn't matter. It should be rich. I don't care where the richness is coming from. Even if they are non-meaningful sentences, if they are phonetically rich, it is fine. In English, if I create a non-meaningful sentences, I ink bottle eat electricity. Let's say I say something like, I ink bottle eat electricity. It does not have any linguistic or semantic sanity at all. But if it is phonetically rich, I will be more than happy to collect it. Meaningful sentences are required to keep the prosody going on, because if sentences are non-meaningful, we'll have more pauses in between. There will be more breaks in between, which will again bias the ASR systems while training. So that's why meaningful sentences are required, but I don't care where the phonetic richness is coming from. So domain is only important when I am using that linguistic aspect. Once it is transformed to linguistic domain, once I have transcribed the utterance to a linguistic domain and creating a dictionary, then probably domain would be important. But otherwise, I don't think domain is that much important. That if demography is, if it makes a difference of the demography, let's say you're only using speech from a certain dialect, whereas you are testing it on another dialect, then domain would be important. Like there are two distinct non-overlapping sets over which it is trained and tested. But if otherwise, if they are just creating a system, I think
Yeah.
domain is okay.
Yeah. Thanks for your explanation.
Thank you.
So yeah, so if no more question, maybe would like to session chair can thanks, and we can then maybe end the session. But yeah, it's really, I'd like to thanks Ravi for all the, it's a nice explanation, and to understand the basics, and also I think clarifying all the questions.
Thank you for giving me this opportunity. Actually, I'm quite happy, and I hope I was able to explain some of that.
Yes, thank you, Mr. Ravi Shankar, Dr. Ravi Shankar Sari. So
No.
definitely,